Hello, in this video we are gonna go over the solution of the problem 221, maximal square. Imagine that we are given a matrix like this and we are gonna find the maximal square. We can start from this square here, and for this one we have one square here, or we can have one here, we have one here, and so on. We can also have 2 by 2. For example, here I can have a 2 by 2, or this one, or maybe here I can have 2 by 2. And we are looking for the maximal square, so the maximal square is this one, which is 3 by 3, and we are gonna return 9. Okay, we are going to use dynamic programming for this problem. Let's consider this cell here. What is the square size for that? So that is 1. So in DP we put that 1. How about, for example, this one? What is the square size for this one? So that is 0. So because it's a 0, we can't have a square over there. So we are gonna put 0. How about this one? That is 1. We can have a 1 square here. So you can see, for example, for all of these elements on the right side, this one I can put 1, this one I can put 1, and for this one it is square size 0, and for the last row this one is 0, so I put 0, this one is 1, I put 1, this one is 0, I put 0. Okay, so we could say if grid ij equals 0, we can just put the value of dp at that location 0. We could say dp ij equals 0. Okay, now consider another cell. For example, this cell. It's 1 inside that, so for sure we have size 1. But can this cell merge to the other cells around it and create a bigger square? So we check that. So we look at the right, and we see that on the right side here it is 0. So it was not possible. There were no square over there. Here is also 0 on the down. So it's not possible to merge. So we are gonna check 3 things: right, down, and diagonal to the right. And when we see there is a 0 there, so it means that it's not possible to merge to any other square. So we are gonna put as 1. Okay, let's consider another one. For example, this one. So again, inside that is 1. So we look at the other things. So we look at here, we look at here, we look at here, and see there is a 0 here. So it's not possible to create a bigger square for us. So we are gonna end up having 1. So it seems that we can create a formula. So for example, we could say dp of I and j equals, so I'm considering 3 parameters. So I'm considering dp of I plus 1 j, so 1 row down, same column. I'm considering dp of I j plus 1, same row, 1 column forward, and diagonal element I plus 1 j plus 1. So I'm considering these 3 elements. Okay, let's go forward and create our formula gradually. Okay, now let's consider this cell here. Okay, so for this cell, what we are gonna look is here, here, and here, and we see all of them are 1. So it is possible to merge this cell to the cells around it and make a bigger square. So we can create this one as a 1 square. So here I'm gonna return 2. So I have these 3 elements. I consider them minimum, and I'm adding 1 because we are increasing the size of the square now by 1. So it was 1 here, 1 here, 1 here, but then it got 2 because now we can expand it and make it 2 by 2. Okay, now we have our formula. Let's go forward. For this one, it's again 2, 1, 1. Minimum is 1, plus 1 is 2. For the other one, 1 is 2, 1, 0, it's 0, so I'm gonna it's gonna minimum is 0, plus 1 is 1, so it's 1 here. And again for this one, I consider this element is 1, 1, 1, 1 plus 1 is 2. I have 2 here, and this is true. You can for example check that this is gonna create a 2 by 2. Okay, let's consider another one, this one. So on the right side is 2, diagonal is 1, down is 2, so I can have minimum as 1 plus 1 is 2. So this one is 2. Now for this cell, so right is 2, diagonal is 2, down is 2, so minimum is 2 plus 1 is 3. And that's true because now I can have this giant square as my result. Okay, let's continue for the other one. So right is 3, diagonal is 2, down is 1, 1 plus 1, 2. I can have 2 here. This one, 1, 1, 2, minimum is 1, plus 1 is 2. For the next one is 0, we just return 0. For this one is 1, minimum of 0, 2, 3 is 0, plus 1 is 1. And the last one is 0. So we found 3 as our maximum, and we return 3 by 3 equals 9 as our output. Okay, we are going to have a function called maximal square, and the input to that is grid. The first thing that we are going to do is to define the number of rows and number of columns. So number of rows is the length of grid, and number of columns is the length of one of the rows, for example the first row of the grid. And now I'm gonna define dp and as an empty matrix. So I say dp equals 0 for I in range of number of columns, and then this array for j in range of number of rows. So this is gonna give me an empty matrix with the size as grid. And then we are going to fill out this dp. Okay, let's go back to the drawing board. As we saw in our solution, for the last row, for example for this one, if the element is 0, we put 0. But if element is 1, we put 1 in our dp. Also for the last column, if it is 0, we just put 0. But if it is 1, because there is nothing on the right side to merge with that to create a bigger square, we can just put 1. So technically for the last row and last column of our grid, we can just copy paste in our dp. Okay, let's do that. So we say for r in range of number of rows, dp of r for that row for the last column equals grid for the same row and last column. Just consider that because this grid that is given to us, the elements are a string. We just need to change them to integers. So I say integers of grid. Okay, and same thing for columns. We say for c in range of number of columns, dp of last row for each column equals integer of grid minus 1 last row different columns. Okay, now we have the last row and last columns of dp ready. We are gonna start filling out the other elements. We are gonna go over all of the elements one by one. So we are gonna have a nested for loop. We say for r in range of r minus 2, because we already calculated r minus 1, and 2 minus 1, and in a reverse order. And we say for c in range of C minus 2 to minus 1 in reverse order. So in our formula, we said that if the grid value is 0, we can just put the value 0 in our DP. So we say if integer of grid R C equals 0, DP R C equals 0. Again, wherever we have a 0 in our grid, we can't have a square. So in our DP, we are gonna put 0. And if it is not 0, if it is a 1, so in that case, we are gonna follow our formula. So from the formula, we saw that dpij equals 1 plus minimum of the 3 blocks on the right, down, and diagonal. Okay? So we say dp of R and C equals 1 plus minimum of dp of R plus 1 row below, same column, dp of R, same row, 1 column forward, and dp of R plus 1 and C plus 1 column forward. Okay, this is our formula. Now we are going to record the maximum value that we calculated in our DP. So we calculate different values for DP, for example 0, 1, 2, 3. So we want to find the maximum. So we need a variable to record that. Let's create that. So at the beginning, I'm gonna define that answer equals 0. And then in our for loop, after I'm done with DP, I'm gonna update that answer and say answer equals maximum of answer and DP R and C. So at the beginning answer is 0, but as we go forward, our DP could turn to different values, could turn to 1, 2, 3, and we always compare that to the previous answer and update the answer over time. And at the end, we are gonna return answer to the power of 2, because what we need to provide as the output is the area of that maximal square. So for example, if we found DP as 3 as the maximum, we are gonna return 9. Okay, there might be also a case that all of these DP values here for this section, all of the DP related to them be 0. For example, in my matrix, all of those elements are 0. And then I have some ones in our last row and last column. So I should make sure that I'm updating the answer also considering the last row and last column. Okay, for doing that, I just need to update my answer. I say answer equals maximum of answer and DP R minus 1. For the column, same thing. I say answer equals maximum of answer and DP minus 1 column. Again, this is just happens when all the elements that are not last row, last columns are 0. So there might be a 1, 1 happening somewhere, and I need to update the answer, because if we don't do that, our answer remains 0, and you might have 1, 1 in our last row or last column. So that's just because of that. Okay, if we run the program now, we can see the answer, and answer is 9 because we have a 3 by 3 square, so the area is 9. That is what we are returning, and that is what we expected to return. Okay, now let's talk about time and space complexities. The time complexity of this problem is order of n, where n is the number of elements in our grid, and the reason is that we are visiting each cell only once, and the space complexity is also order of n because we created this DP to record the intermediate solutions. Okay, this is the solution of the problem 221, and thank you so much again for watching this video.